For the rest of our acid-base unit, we are going to be looking at titrations of various acids with bases and determining the pH at various points during the titration. And determining the pH all depends on the identity of the chemicals in your solution at that time. Whether it's an acid or base and whether it's weak or strong will determine how you find your pH. So we're going to go through various examples of how to find the pH of these different solutions. So this is really just a review. It's nothing too new. So for example, let's say you have a strong acid in your solution, such as HCl is a strong acid. Remember, if it's strong, that means it ionizes 100%. And so every single hydrogen ion will come off of every single HCl in the solution. So finding the pH of these solutions are actually the easiest because, for example, if you have a 0.2 molar HCl solution and every single hydrogen ionizes, then the concentration of hydrogen is also 0.2 molar. So you can find the concentration of hydrogen straight from the acid and just take the negative log of that for your pH. Keep in mind that if there was a 2 there, such as an H2SO4, the concentration of hydrogen would be 0.4, not 0.2. In this case, for HCl, the concentration of hydrogen would be 0.2. A strong base works similarly, 100% ionization, except this time it contains hydroxide, an example being sodium hydroxide. So let's say we have a 0.1 molar solution of that. Every single hydroxide will ionize in the water. So the concentration of hydroxide will also be 0.1 molar, and from there you can go on to find your pH. But since you have your hydroxide concentration and not hydrogen, you'll actually, from your hydroxide, find POH, and then from your POH, subtract 14 to get your pH. Now, when you have a weak acid, remember, about less than 10% ionizes. So we cannot figure out the concentration of hydrogen directly from the concentration of the acid. So if you have like a 0.1 molar HF solution, the concentration of hydrogen is going to be much less than 0.1. So to figure that out, this is a Ka problem. So you would set up the breakdown equation of the HF. So I would just do like a tiny little example. HF will break down into hydrogen and fluorine. And if we're interested in the pH, we got to figure out how much hydrogen breaks off from this. So you would make the amount of hydrogen that breaks off X. And of course, you'd have to know the Ka to solve for X, which would be given. And once you find X, X is your concentration of hydrogen. And from there, you can take the negative log of that. Now, with a weak base, again, not about 10% ionizes, so, or it truly actually just steals the hydrogen from water. An example would be 0.1 molar NH3. So this would be a KB problem, where you would show the NH3 acting like a base. In this case, you have to show it reacting with water to do so. The hydrogen transfers from water to NH3, and that makes NH4 plus and hydroxide. So in this breakdown equation, if you solve for X, this is going to be of hydroxide, not hydrogen, because again, this is a KB problem. It's a weak base. So X is going to be hydroxide, and if you take the negative log of that, you'll find POH, and then after that, you can find pH. So very similar to the Ka problem, except X represents hydroxide, whereas in a Ka problem, X represents hydrogen. All right, now the next kind of solution that you might come across would be a weak acid and its conjugate base pair. So for example, if you have NH4 plus and its conjugate base NH3, as long as they're in similar concentrations, you got yourself a buffer. So you'd use Henderson-Hasselbalch. All right, now the next two situations are a little bit more unique. We have a strong acid and a weak acid combined. Now acids don't react with each other, but you'll have HCl and for example, NH4+, and let's say they are similar concentrations. Which one do you think is going to have more effect on the pH? The strong acid should definitely have much more of an effect on the pH. So since the weak acid's effect is pretty much negligible, we will treat this like a strong acid situation, and we don't even care about the weak acid that's present. So you would carry on as just as if it was a strong acid. So you just take the hydrogen from the concentration of your strong acid, from the molarity, whatever molarity it is, of your strong acid, and then take the negative log of that, just like you did up here. Now, similarly, if you have a strong base and a weak base, like sodium hydroxide and NH3, and as long as they're in kind of similar concentrations, the strong base is going to have much more of an effect on the pH than the weak base. So we can ignore the fact that the weak base is present and just treat this like a strong base situation. So we can figure out the concentration of hydroxide from there, find the POH, then pH. All right, so this is going to be how you find the pH of various solutions. So we're going to be applying this to the concept of titration. Now, we already know that titration is essentially just a neutralization reaction and stoichiometry. So whenever you think titration, it's stoichiometry. But we will not only be figuring out the molarity of solutions, you could also use titrations to determine the Ka of an acid or the Kb of a base. So that's a new twist that we're going to put on titrations. Again, we titrate until the reaction is complete, so that is the equivalence point. That is when we have the perfect mole ratio of acid to base. There's no excess reagent and there's no limiting reactant. So imagine that we have a reaction between an acid and a base, such as this. When we are at the equivalence point, all of your acid and all of your base has reacted away in the perfect mole ratio. No excess reactant, no limiting reactant. So those are all gone. You're only left with the products. So the pH at the equivalence point is determined by the identity of the products. So how do we know when to stop titrating? Well, it's really the drop that you add extra after the equivalence point. That's what changes the color of the indicator. So an indicator has to be added to the flask so that you know when to stop the reaction. And there's so many different indicators out there. And the end point, the pH that is at the end point is what you want to match your indicator. So certain indicators will change colors at certain pHs, and you want to turn the indicator's color at whatever pH the end point is. So let's say the pH of the end point is like a 9. You want to look at your list of titrations. It's actually on the back page of your homework. So you want to look at your table of indicators and choose a pH for that. Unfortunately, I don't have that on me, but you can look there yourself. So take a moment and read that, and I'll post a next video for the back page.